Welcome back. This is the first of two lectures where we're going to talk about a proof outline for interior point methods, the basic steps that we need. Let's recall the basic formulation that we need, in addition to the three main objectives that we need for the flow of interior point methods to work. So recall that we have our barrier function, which I'm going to denote by f0 of x. And this barrier function goes to infinity when we approach the barrier of our set. So for linear programming, and in particular for the linear programming constraint ax less than or equal to b, we're going to use the barrier function f0 of x equal to minus the sum over the m constraints that we have, I equals 1 to m, of log of bi minus ai transpose x, where ai transpose is basically the row, the ith row of the matrix A. And recall also that we're then going to write down our function ft of x, which is t times the original objective of the linear program, t times c transpose x, plus f0 of x, our barrier function. And xt is, I write as an element of, but by the strict convexity of f0, we know that it is that this is the argument is unique. So xt is the minimizer of ft of x. The three key objectives we need is first to show that we can optimize ft quickly. In particular, what that means is that we can use Newton's method and enjoy the quadratic convergence regime. Step 2 is to show that we can increase t quickly. And quickly here is going to mean at a geometric rate. So our update to t is going to be, we want it to be, some multiple that's bounded away from 1 times t. And of course, we could increase t as much as we wanted, but what is the key point, keeping in mind the objective of step 1, is to show that we are still in the quadratic convergence regime. While staying in the quadratic convergence regime. So specifically, what does that mean? xt is the argument of ft of x, and it is going to be the initialization for when we update to ft plus. So we need xt to be in the quadratic convergence regime of the function ft plus of x. Intuitively, if we increase t just a little bit, their optimal solutions should be very close, but we want to see how much we can increase t. And then finally, step 3 requires us to show that c transpose xt minus c transpose x star being the optimal solution of the original LP, the full LP formulation, is small. This quantity goes to 0 quickly. So these are our 3 steps. Let's remember now the key definitions that we have and that we're going to use. The most important that we're going to see and make great use of is this local norm. And recall, this is what we needed in order to make, to replace the Euclidean norm with an affine invariant norm. This is defined as the Euclidean norm of H, but subject to the affine transformation that we get using the Hessian of F, which, recall, is just defined as H transpose times the Hessian of F times H. Now you'll notice that I've written F0 here, but for us, you'll note that Ft differs from every other Ft prime just by a constant multiple of t. So in other words, this is equal to F0 for every t. And we use this local norm to give an affine invariant definition of Lipschitzness, or an equivalent, an analog, not equivalent, of Lipschitzness. So recall that we said that function f is M self-concordant if the third tensor of f at x, evaluated at u, is bounded above by twice times the constant m in the definition times the third norm of h, but which norm? The local norm. Now we move to quadratic convergence. Once the gradient of f in the Euclidean norm is small enough, then we are in the region of quadratic convergence. Oops. So we're going to replace that with a local norm on the gradient. But it's not going to be quite the local norm. It has to be the dual of the local norm. Just like when talking about mirror descent, when we're looking at a norm on gradients, we use the dual norm. So I'm going to replace it with the local norm. And the key definition, this is so important that we're going to just give it a different, give it its own notation. Lambda subscript f at x, I'm going to define it to be exactly what's written there. So this dual local norm, and this is sometimes called the Newton decrement. You may see that word in the literature. So there are two key things that we need to do. So recall that for Newton's method, we use strong convexity to say that as long as the gradient is small enough, then we must be close to the optimal solution. Again, the rationale is that we can test the gradient being small, but we don't know where the optimal solution is. So that's going to be the first step. And then finally, we'll show that as long as we're indeed close enough, then we have quadratic convergence. So the lemma that we need says that if this quantity that we just wrote is less than 1, then x minus x star, the optimal solution, again, this distance is evaluated using the local norm at x. And note, of course, this is not the dual norm anymore because I'm measuring the distance of points. This is at most something that's controlled, again, by a similar quantity. So this is what replaces that first condition that we had for Newton. And then the theorem guarantees that we have quadratic convergence as long as x is close enough to x star. And how is that measured? Again, using the local norm and using this Newton decrement. So if the theorem says, as long as this quantity is small enough, in particular, as long as this is bounded above by 1/4, then for the update on x being given by an undamped Newton step, namely x equal to x minus the Hessian inverse times the gradient of f of x, then we're guaranteed that this value is less than 2 times lambda f of my previous point x squared. So comparing to what we saw for Newton's method, again, this is not a geometric convergence rate where we're looking for this multiplier here to be something small. We don't care about that. What is really important is this square here. So what you can show, very similarly to what we did for Newton, is that this implies that if we take k steps of Newton's method, then we get to xk plus 1. And this is going to be bounded by 2 to the 2 to the k of lambda f of x1 raised to the 2 raised to the k. And here we use this assumption that x1 satisfies this condition here. So as long as lambda f of x1 is less than 1/4, what does this tell me? This implies that lambda f of xk plus 1 is less than 1/2 raised to the 2 raised to the k. How do we bring this home finally? We use the lemma from the previous page. So now, using the lemma, we have that xk plus 1 minus x star is bounded above by lambda f of x k plus 1 divided by 1 minus lambda f of xk plus 1. The denominator is basically going to be 1, and the numerator is going to be 2 to the minus 2 to the k. So this is what we want here. So this establishes, well, we didn't give the proof, but this lemma and this theorem establish basically step 1, that we have quadratic convergence. So what's left is to show now that I can update t at a geometric rate and still stay within the region of quadratic convergence. And we're going to need some additional conditions for that, and we're going to pick that up. Next time.